So for understanding the joint moments, one must recall whatever we have learned into the previous 3 videos. The first video and the second video was dedicated to the only one random variable. So thereupon we had the simple experimentation for flipping a pair coin, rolling a pair die, or a roulette wheel. Roulette wheel was of course with respect to the continuous values into the interval 0 to 1, but the pair coin that results into either heads or tails, or the another example of rolling a pair die that results into the 6 values 1, 2, 3, 4, 5 and 6. The 6 surfaces of that particular die are the examples with respect to the discreteness there. So thereupon, for such experiments having the representation by random variable simply x here, the ensemble averages we have discussed as like the mean or expected values, the mean square values here. After that, the variance was also studied and the standard deviation here. As in the previous video, we have extended the number of random variable with the extended complexity into the experimentation also. So here the parameters of the ensemble averages that are required without not having the thorough understanding of the probabilistic processes here, we must have the joint moments here. So there are 2 parameters or the 2 averages we must call them, and these are very much important, hence primarily we take them, and these are nothing but the correlation and the covariance here. So here for the 2 random variables, if you take the cases by small x and small y, that time the correlation can be denoted as small r in the suffix x comma y here. So here this is the correlation basically of second order joint moment here, and the mathematically it can be obtained by having the expected value of the multiplication of x random variable with that of the complex conjugate of y here. So this is the mathematical simple way to obtain the correlation. So correlation is the first ensemble average or the primary average with respect to the joint probabilities. Now moving to the second average here. So correlation, there it is the covariance, and as correlation is denoted r suffix x comma y, covariance can be denoted by c suffix x comma y here. So this covariance can be obtained by again taking the expected value, but this time this expected value is not mere onto the multiplication of x with the complex conjugate of y, the random variables here, but the difference of x with that of mx and y with that of my, then the bracket is having the complex conjugate taken here. So what are these small m suffix x and small m suffix y? These are again the means or the expected values. So in this particular formulation, you can come to see that individually the expected value of random variable x, the expected value of random value of y, variable y, have been taken, and the difference of the random variables with these expected values have been taken, and these differences for the x and the difference having the complex conjugate computed for the y has been taken to be substituted into the previous formula for the correlation that will give us the covariance here. So this is again for the second order and the joint moment here. So if in this particular formulation of covariance we obtain the values of the expected values for x and y to be the zeros here, this will be the same formulation of correlation. Now we shall move forward to utilize the formulation of covariance into the practical cases here. So it is quite convenient to have normalization of the covariance. The normalization of the covariance formulation offers the advantages of having invariancy into the scaling. So the scaling we can limit to the maximum value of 1 which is more convenient. The normalized representation of the covariance formula will be giving rise to a new coefficient, a variable what we can call, most likely it is known by the name correlation coefficient, that we generally represent rho suffix xy here. So x and y are the two random variables, and now it can be computed as a ratio. So for normalization purpose, what we used to be doing into the covariance, that we have substituted into the numerator, and for normalization purpose we divide this numerator by the multiplication of sigma suffix x into sigma suffix y here. So as the ensemble averages with respect to the single random variable we have learnt into the second topic, the sigma suffix x square is nothing but the variance, and when we take the square root of the same, that is nothing but the standard deviation here. So these concepts can be the same here in this formulation, and the modified formulation from the numerator point of view we can also make to the form expected value of the multiplication of x with that of y conjugate, which is the correlation here, and the difference of this correlation can be taken with the multiplication of expected values of the random variables x and y, hence mx along with my conjugate we can represent here. So in this regard, for the values of means to be 0 here, for 0 mean random variables, the correlation coefficient gets to the form, that is rho suffix xy is equal to expected value of x into y conjugate, that is the correlation, divided by sigma suffix x into sigma suffix y. So because of such a normalization, the correlation coefficient is bounded to the upper value at 1 here. Hence we can write mod of rho suffix xy is always and always less than or equal to 1 here. So this was all about the joint moments, the two very important correlation and covariance we have addressed, and the another hybrid form from the two after normalization, that is correlation coefficient. Basically in many of the applications, correlation coefficient is utilized to understand the extent of similarity between the two, the reference and the practical variable that we are processing so far. So these were the joint moments.